Thank you very much. It's a pleasure to be here. I'd like to start by thanking Fernando and Lucas for the invitation. And as Lucas already mentioned, I'm a little bit of an outsider and usually look at Riemannian problems from a symplectic point of view. And sometimes this is useful. So I'd like also to mention that all results I'm going to mention today are joint with Alberto Hryniewicz, Barney Bramham, who is also a member here, and Pedro Salomão. So my goal is to explain a little bit the relations between systolic geometry of surfaces and symplectic dynamics on surfaces. Basically, the model of these, the relations, the underlying principle here is that a systolic inequality can be sometimes translated into some kind of quantitative fixed point theorem for area preserving maps on a surface. Okay, that's the summary of everything about the new results I'm going to mention today. So let me first start by a little bit of history from the Riemannian side of the story. That's a Riemannian geometric side of the story. So systolic geometry started in 1949 with a result due to Loevner. So to state the result, let me first define a little bit of notation. If you have a closed manifold, I'm going to denote by L mean the length of a shortest non-constant closed geodesic I'm going to denote by Cs by 1 the length of a shortest non-contractible loop, and by C's H1 the length of a shortest non-null homologous loop. So Loevner's result states that C pi 1 square divided by the area is less than or equal than 2 divided by square root of 3 for all metrics in the two torus. And one has equality if and only if we're talking about R2, the flat metric given by R2 divided by the hexagonal lattice given by the lattice spanned by the corners of an equilateral triangle. Okay. And so there's a quote by Gromov asserting that this is an amazing discovery. The second fundamental result is acknowledged with that of Poole, asserting that c pi 1 squared divided by the area is less than or equal than pi over 2 for all metrics on projective plane. With equality if and only if we're talking about the round S2 divided by plus minus 1. So in these cases, not only the inequality is very nice, but the fact that one can characterize the maximizers of this ratio. One should also mention result of obtained independent by Blatter in 63 and Bavard 88 for the Klein bottle. For all metrics in Klein bottle. And apparently it seems that the maximizer is either not known to be smooth or actually, let's say one has examples of metrics achieving this maximum, approximating this maximum, but they converge to some singular metric. And also, I'd like to mention Ebda and Burago, also kind of independent, asserting that systolic, this ratio is not larger than 2 for all non-simply connected surfaces. Gromov studied this problem and obtained sharp asymptotic behavior of this ratio when the genus grows. So actually here, one use the cis-H1 ratio. Let me recall precisely the statement. Here one finds a universal constant times log of the genus squared divided by G. So it's asymptotically this is sharp. Okay. And then in the early 80s, Gromov obtained a very nice, very strong result for all dimensions, where he proved that on Arlenberg-MacLane classifying spaces, one has an inequality of the following form. Yes, the result is slightly more general than what I stated here, but I'll keep to this. I stick to this one. And okay, and of course, an important question. This subject is to study sharp upper bound for these ratios. even for surfaces, this is not, I mean, except for these results, this is not computed. Any questions about the statements? Okay, so all these results, they leave the two-sphere out of the picture. So, in general, I'll denote by rho c is the systolic ratio of a closed Riemannian manifold, the ratio between L mean divided by volume. Okay, and for the two-sphere, computing the sharp upper bound here is very difficult problem. Should mention result by Krook. Stating that the supremum among all Riemannian two-spheres of the systolic ratio is finite. So there is systolic geometry also in the two-sphere. And the question is, what is this number? That's this question in this particular context. So a very hard problem. Well, his proof, I think here, I mean, the outcome of his proof, if I'm not mistaken, one gets this upper bound. But of course, it's not, well, it's very much not sharp one. And question is, what does one know about this problem? So this question can be interpreted in two ways. I mean, this question has two different answers. I mean, if you can ask what does one know in terms of what can be proved or of what was proved, and one can also ask what does one know in terms of, I mean, what can we see in examples? I mean, how high can we go by exhibiting an example? So this is two different ways of interpreting this question. So the best upper bound, in the sense that it's been proved to be some upper bound, is due to Regina Rotman. And one can exhibit metrics for which the systolic ratio is getting close to 2 square root of 3. That's the Calabi-Krook sphere. So this is interesting because, I mean, if you, let's say, if you look at this result of Poole, you might wonder if the round geometry will maximize the systolic ratio. And the systolic ratio for the round metric is pi, but pi is less than 2 square root of 3, which means the answer is no. There is no analog of Poole's result for the two-sphere. So let me describe the Calabi-Krook sphere. One takes two equilateral triangles, flat equilateral triangles, and think of them as two hemispheres of a flat sphere. So this is not very equilateral. Let's pretend it's equilateral. Right, so the geodesic flow, of course one can take this singular picture and fatten it a little bit, round the corners, and one gets a even positively curved two-sphere, for which the geodesic flow is in some sense converging to the Beer flow. When you get near to this face, you go to the other side, then you go to the other side again, and so on. And here you see that one sees that the minimal non-constant closure geodesic is converted to the length of these two bounce orbits. So the systolic ratio, let's say if the side is L, this is equal to what? Square root of 3 times L divided by, well, you don't divide by 2 because you're taking twice the height, and then the area is twice the area. So you get, if this is right, you get 2 square root of 3. Okay, so it's interesting to see the connection to billiards here, and one might ask an analogous question for billiard tables. One can ask, well, given a T convex body on R2, one can look at the ratio length of shortest periodic billiard trajectory divided.
When you're approximately a triangle by like a sphere, I'm assuming the systolic ratio goes down.
Sorry?
If you smooth it out, like you take this positively curved sequence of spheres,
It goes down.
goes down.
Yeah. Oh, at least in this, I think you're probably thinking of the same smoothing procedure that I'm thinking. I mean, if you're thinking about the same smoothing procedure, then it goes down. I mean,
So it could be too further field.
that's actually conjecture. I forgot to mention. Conjecture. The soup. So then, one can also consider this problem, looking at billiard tables on the plane and trying to compute this. So if you, I have been discussing this problem a little bit with Ostrover and Brahman, and it seems that it's really hard. And if one looks at constant width tables, then the hello triangle is a maximizer. But it seems that the computer wants to make us believe that you go up from the hello triangle. So it seems to be hard. I don't know. Okay. Sorry?
Can you prove that the width is finite?
It's finite. By very abstract nonsense, you know, convex bodies, they can be compactified in the right topology and so on. And this, I mean, both of these quantities are continuous in the right topology. Okay. So we saw here that the Calabi-Crook sphere is not the round sphere is not a global maximizer because you have the Calabi-Crook sphere with a higher systolic ratio. But then one might ask if the round geometry is a local maximizer. So then this led Babenko and Balachev to conjecture that, you know, the round geometry is a local maximum for the systolic ratio. And so one of the results I'd like to speak about today is the confirmation of this conjecture, but with a little bit more input, output, let's say. If the Riemannian two-sphere is delta pinched for some delta bigger than the following constants. Sorry. This is about 0.83. Then one has the following chain of inequalities. One has L mean square less or equal than pi times area, and this is less or equal than L max square, where here L max is the length of longest embedded closed geodesic. And moreover, if one of these inequalities is an equality, then the metric is Zoll. And by a Zoll metric, I mean one for which all geodesic rays are periodic, and they have the same length. So that's the difficulty of proving the conjecture is exactly because you have plenty of Zoll metrics near the round one, which are non-isometric to each other. And whenever one has a Zoll metric, one has a systolic ratio equal to the round two sphere. So you have this large infinite dimensional set of metrics, very much non-isometric to each other, which are all local maximizers, which are supposed to be all local maximizers. And today I'll try to explain a proof of this theorem where we actually improve this pinching constant. I want to make this better today. Maybe there is a mistake, but then hopefully not. Okay.
So the billiard problem, when can you approximate by smooth test? Does the triangle?
Well, this is kind of a folklore statement that everybody believes, but I think there is no published proof. So I think always. Well, at least the boundaries piecewise C2 say, I think always. Unless there is some very ugly boundary for each of the table for which some problem arises. But I'll be fairly confident to say that if the boundary is piecewise C2, then.
So you could apply a Crookes here.
Yeah. Of course, there is a little bit of a factor here because the area of the table is half the area of the matrix of the sphere. Okay. I would just like to mention a result by, so in particular, the result implies that if all lengths of embedded close geodesics coincide. So then we are in a Zoll situation, provided that we are under this pinching condition that's implied by this theorem. But I'd like to mention one nice result due to Marco Mazzucchelli and Stefan Suhr, stating that this actually holds for every metric. I mean, we know this actually holds with no pinching condition. So that implies this result for under the pinching condition. Okay. So the pinching is an interesting parameter. One can then think of the following problem. One can define a function of the pinching constant. So this would be the supremum among systolic ratios of metrics which are delta pinched. Maybe I should say that delta pinched means that the minimum of the Gaussian curvature is at least equal to delta times the maximum of the Gaussian curvature. That's what it means to be delta pinched. So and then the question is, plot the graph of this function. So for Zoll metrics, we get 1. Although Zoll metrics don't need to be 1 pinched. But then if we relax the pinching, you go all the way down to 0.83. So this graph does this, and here we don't know what it does. Of course, it's a non-increasing function, and here it converges to a number bigger than 2 square root of 3, but smaller than 32 in view of Rotman's result. So today I will explain a little bit how to make this graph look like constant pi for a slightly lower value. But I think an interesting question is this one. Is 1/4 pinched enough to guarantee that you get a systolic ratio bounded by pi? I think that's a more, let's say, down-to-earth question. Okay. Another result I'd like to mention, maybe I'll state it here, is that the systolic ratio is not bigger than pi for all spheres of revolution. So you can have very much negative curvature, can be some quite crazy sphere of revolution, but you don't go above pi. And also here, again, equality if and only if metric is all. Okay. So now, are there any questions for? That's the end of.
A little bit confused. How is it possible that the limit there is slightly bigger than 2 square root of 3? So isn't that conjecturally the...
Conjecturally is equal to square root of 3.
Right, but if you had a sequence of examples going above, then the conjecture would be violated, right?
That's right. Yeah, no, you're right. I mean, if the conjecture is false, maybe
Oh,
the conjecture.
Great or
Maybe greater.
Ah, okay, because if you write
Sorry.
it like that, then
Sorry, yes, you're right. Yeah. Okay. Yeah, we don't want to rule out the conjecture too soon, right? Okay. So that was the end of my Riemannian, say, introduction. Now I'll jump a little bit to the systolic geometry part of the talk. So I would like to study the following setup. I'm looking at an exact, compact, connected, symplectic surface. Exact means the symplectic form is exact. So a symplectic form in dimension 2 is just an area form. So in particular, the boundary is non-empty. And one has the group of symplectomorphisms, which are the diffeomorphisms of this surface which preserves the 2 form. And it contains, so one might want to look at the connected component of the identity. Which happens to be endpoints of smooth symplectic isotopies starting at the identity. It's not entirely obvious, but it's true. And we then will look at its universal covering. So here, concretely, I will be looking at smooth symplectic isotopies starting to the identity, from the identity ending somewhere, up to homotopy, keeping endpoints fixed. And one might ask, is this group simple? And the answer is no. One has a flux homomorphism, a non-trivial one, to cohomology modulo the boundary. And it's very easily describable. If you have such an isotopy, and if you hit the flux on a cycle here, that's equal to the omega area swept by the isotopy and the curve. And then so this means this group is not simple. So then you ask, is the kernel simple? And the answer is again no. The answer is no because one has a Calabi homomorphism. And so let me describe it as a Calabi. So if the flux is 0, you might want to try to solve the following boundary value problem. You might want to try to find a function which satisfies this differential equation. So here lambda is a primitive of omega, and boundary values are given by the integral of the point along the isotopy of this one form. That's called the action induced by the isotopy and the primitive, and the Calabi is the average action, or well, let's say I don't take the average, just integrate the action. Okay. So you might want to keep the following picture in mind. If you have a nullus generator of the relative homologies, a line connecting the boundary components, so the map is the isotopy is going to twist this curve, and then the omega area, with signs of course, is equal to the flux. So if this is 0, you can define this average action. You can define the action and take its average. So you see, for instance, that rotations, they are not in the kernel of the flux. So the fact is that, of course, I might wonder, does Calabi depend on the primitive? So Calabi does not depend on choice of primitive. Also, if you take a fixed point of the end map, and I'm assuming it's null homologous. This means that if you take the so here's a fixed point. If you run it around with the isotopy, you come back to the initial point, and then being null homologous means that this loop is 0 in homology. So if you have a null homologous fixed point, then the action value also does not depend on lambda. Okay. So you might want to look at this picture with eyes from ergodic theory. You might want to ask, okay, here's a function. The Calabi value is its average. So for almost, by point-Poincare recurrence, from almost points, you know, the time average of the action is equal to the space average, which is the Calabi. So can you take, among these almost set of points, can you take almost all set of points, can you take a fixed point? Probably no, right? Can you take a periodic point? Then it becomes harder. Maybe not also. But this is exactly the kind of question you have to ask in order to apply these methods to systolic geometry. So the question is, suppose that you have an isotopy in the kernel of the flux. Suppose that the endpoint is not, well, suppose that the Calabi is less or equal than 0. Endpoint not the identity if Calabi is 0. And then the question is, does there exist a null homologous fixed point such that the action at this fixed point is less than 0. So you might look at this question and you might wonder, what does it have to do with systolic inequalities? And this is exactly the systolic inequality hidden in symplectic language. Okay, so we try to somehow answer positively a question whether does there exist at some kind of quantitative fixed point theorem. So let me, for the first hour, for the end of the first hour, I'll try to explain the connection between these two questions.
So is there an actual way to come up with a
Yeah. If you take a Hamiltonian, perhaps time-dependent Hamiltonian, and if your Hamiltonian turns out to be, say, 0 on boundary, and the non-trivial The non-trivial assumption here is in the case where the boundary has more than one component. I mean, the boundary has several components. If you take a Hamiltonian that's 0 on all boundary components, and then you consider the Hamiltonian isotopy generated by this, these are exactly the guys in the kernel of the flux. So these isotopies, if it's in the kernel of the flux, this is equivalent to saying that it's the end point of an isotopy generated by Hamiltonian, which is 0 on the boundary. Yeah, in terms of the Hamiltonian, yes. Actually, one gets the average of the Hamiltonian, but then the Hamiltonian now, you have to also average on the time, which the Hamiltonian depends on time. Okay. So, of course, this is the answer is no in general. For the same, for the, you know, sort of the fact that this answer is no in general is related to the fact that the round to sphere or Zoll metrics don't maximize the systolic ratio. But sometimes it is true, and let me describe one setup when this is true. So suppose we're talking about a standard annulus, and so you have an isotopy for all these properties. And then you have to make one further assumption. Suppose that the time one map is monotone. Monotone in the sense that it maps, so let's say here's the annulus, it maps a straight line to something that goes up. Sorry, it transverse to horizontal foliation. So if you have this technical assumption, then it's true. Then there exists P fixed point, null homologous, with action negative.
So can you say what monotone is again?
Is this condition? If you take a straight line, a line given by, you know, x equals to a constant. It's a copy of this interval here. Then it's mapped to a line which is going up in the sense that it's transverse to the horizontal foliation. So the map can be quite, you know, in some sense it can be very poorly behaved, but in some sense it also has to be not so poorly behaved. Okay. So I'll just jump a little bit ahead of myself and just explain to you a little the connection to geodesic flows on S2. So the connection is through global surfaces of section. And the theorem that allows us to use this gadget, this dynamical gadget, is a theorem of Birkhoff, asserting that if gamma is embedded closed geodesic, and on a two-sphere for which the curvature is positive everywhere, then I'll denote it by A gamma, the Birkhoff annulus, associated to gamma is a global surface of section. So let me draw the picture of the Birkhoff annulus. The Birkhoff annulus looks like the following. You're looking at a positively curved two-sphere with an embedded closed geodesic, which is gamma. Then if you choose a hemisphere, then you on top of each point of the closed geodesic gamma, you put the bouquet of circles pointing towards the hemisphere you chose. Say you choose this one. So on top of all these points, you consider this bouquet of circles, of unit vectors. Then you get an embedded annulus in the unit sphere bundle. And that's a global surface of section for the geodesic flow. For the geodesic flow. In the sense that every, the unit sphere bundles are three manifolds, it's a copy of SO3. And then you have a flow, the the geodesic flow, and this embedded annulus is lying there. The boundary of the annulus consists of periodic orbits, these two geodesics going that way and going that way. And every single trajectory, which is not one of these orbits, will hit this annulus transversally in the future and the past. So you can encode the whole dynamics of the geodesic flow as the dynamics of the return map to this Birkhoff annulus. So now we are already, you see how we are going to connect the geometry to the dynamics through this gadget. Okay, but this I should say that this is implementing a point of view. So this line of reasoning is implementing a point of view advertised by Florent Balachev and Juan Carlos Alvarez-Paiva, which is basically saying that, well, you might want to abstract the systolic inequality for geodesic flow to the more general setup of systolic inequalities for HAP flows in contact geometry, and then maybe in this bigger space, let's say in this more ample point of view, maybe there are different tools that come into play. Of course, you are in danger. You might run into difficulties because it's a much more ample setup. Maybe problems are much harder too. So who knows, right? Okay. So let me define what is a contact form. So here I have some manifold, and then a one form is a contact form. If d alpha restricted to the kernel of alpha is a non-degenerate bilinear pairing every point. So in particular, this force is that's a definition. So M is some manifold. This force is the This forces the dimension of the ambient space to be odd, say 2n minus 1, and then this condition is equivalent to saying that alpha wedge d alpha to dn minus 1 is a volume form. Okay, and All right. If you have such a one form on a manifold, you also have a dynamical system. So there is a unique vector field given by the following, implicitly given by the following equations. It's called the Hebb vector field. And in the case M is closed, one expects this vector field to have periodic orbits. This is proved in dimension 3 by Taubes. I'll take for granted the existence of periodic orbits here in the dimension. And then you can consider the number T mean, which is shortest period among closed orbits of this vector field. You can also consider the contact volume. So I'll take this as a positive number. I'm orienting the manifold by this volume form. And finally, the systolic ratio. Okay, so contact forms have systolic ratios. So if you've never seen this before, I'll just give you one example, which I'm sure you know. So basic example is the following. So if you have any manifold, any Riemannian manifold, so on the tangent bond you have a one form, so-called Hilbert form. So the Hilbert form at a vector v applied to a tangent vector zeta is equal to, the inner product between v and d pi of zeta, where pi is the foot point projection. That's a one form, and this one form is a contact form on the unit sphere bundle. T mean, I should say, very important fact. The geodesic flow of the metric is the Hebb flow, which means that T mean equals to L mean. The contact volume is a constant depending on the dimension. Times the volume of the Riemannian manifold. So you see that systolic ratios of Riemannian metrics are up to a constant depending on the dimension equal to the systolic ratio of the contact form. So then you might ask all standard systolic questions for contact forms in non-dimensional manifolds. So we take this point of view, we have this global surface of section, translate the systolic inequality into some kind of quantitative fixed point theorem, and then try to prove a systolic inequality. That's the plan for the second hour, but I think we should maybe make a pause. Okay. Now, so for the second part of this talk, I'll try to first prove something, and then move on to this more abstract contact geometric inequalities. Okay, so remember that the task is to show that if you have some pinching, then you have some inequality. Let me just state one of them. The other is analogous. So I'm talking about S2 here. So the basic tool is a comparison theorem. So two comparison theorems, so to speak. So the first is Klingenberg's estimate on the injectivity radius. And the comparison theorem of Toponogoff. I'm not going to state the Toponogoff's comparison theorem, but I'm going to state a consequence of it. The perimeter, so a consequence of, let's say, the perimeter of convex geodesic polygon is less or equal than 2 pi divided by the minimum of the curvature. Okay, these are the two comparison theorems. Toponogoff's theorem is about comparing triangles of the same side between the space and the space you're looking at, say the two-sphere you're looking at, and the two-sphere with constant curvature for some constant below than the minimum. And basically, you know, the statement is that the less curved you are, smaller the angles of a triangle with the same sides, right? You might do this thought experiment in R3. I mean, try to draw a geodesic triangle in a certain sphere of a certain radius, and then you draw another geodesic triangle of the same lengths, whose sides have the same lengths as a previous triangle, but in a sphere of larger radius, and you see that in the sphere of larger radius, the angles are smaller. Okay. All right, so we are looking at these embedded closed geodesic, which we know exists by work of Schneemann. I'm going to parameterize, let's say we take gamma so that length of gamma is L min. By the way, there's a result of Crooked saying that for all positively curved two spheres, the shortest closed geodesic can be realized by an embedded. So the length of the shortest closed geodesic can be realized by the length of an embedded one. Certainly for 1/4 pinching condition, this is implied by Toponogoff, so let's not worry about this. So on the Birkhoff-Anolos, we have these coordinates x, theta, right? So x coordinate, these are coordinates on the Birkhoff-Anolos, and they live on R mod L min z and 0 pi. So this angle here, right? We orient the geodesic as the boundary of the chosen hemisphere, then you have this angle, theta. Okay. So you see that the Hilbert form restricts to the primitive of an area form in the Birkhoff annulus, but that's only true in the interior because you see the Birkhoff annulus, the boundary is the geodesic. So, right, the geodesic vector field is the Hebb vector field, which is in the kernel of d lambda. So d lambda is an area form, but it cannot be an area form on the boundary because the boundary is tangent to the Hebb vector field, which is in the kernel of d lambda. If you want to normalize things to work with a non-area form, you might want to consider the as a substitute for the second variable, the number y given by minus cosine of theta, and then here the Hilbert form on the Birkhoff annulus is equal to minus x dy, and omega, the area form, is the x dy. You can do this. The price you pay is that this is a smooth map from this annulus to the same annulus cross minus 1, 1 instead. But it's a smooth map. It's a homeomorphism, but it's not a diffeomorphism. The inverse is not smooth. And if you conjugate the map by this change of coordinates, you end up with it's a smooth map in the interior, and it's not differentiable in the boundary. You lose some partial derivative in the boundary. But it's okay. Everything that I'm going to say works for this in both setups. Either you work with area forms that vanish from the boundary, or you work with nice area form, but with maps which are slightly less regular at the boundary. That's a white lie, I'm telling you. The statement of the fixed point theorem that I made before needs to be generalized to this slightly larger class of maps. Okay. Right, so I'm going to denote by psi the return map, and by tau the return time. Right, so the picture is you start with a vector, let's say here, and then you shoot the geodesic. It's going to go up, then it's going to go down, then it's going to go up again. And that's the image of this vector under the return time. The return map is this vector here, and the return time is the length of the geodesic ray you followed all the way back to the Birkhoff annulus. Okay. Okay. So the first lemma we need to prove is the following. Is 1/4 pinched. Actually, temperature is delta pinched for some delta bigger than 1/4. Then the return map is going to be the time 1 map for some isotopy in the kernel of the flux. So you can choose an isotopy in the kernel of the flux. And so this isotopy here, of course, the kernel of the flux containing it's containing that group, and the corresponding action. So this action is associated to this isotopy and the particular primitive. We're going to always fix the particular primitive of the area form given by the Hilbert form. It's related to the return time by this formula. Okay, so that allows for a dictionary between dynamics and geometry. The corollary is corollary is that the Calabi invariant is going to be the average of, so the integral of this function, which is then the integral of tau minus the integral of this constant, but the total area of the annulus is 2L mean, right? The total area of this annulus is 2L mean. You know, the area, so the standard area of this circle across this interval is 2 times the length of that circle. So you get a 2L mean square here. But you know, by Santa law's formula, this is equal to the contact volume and the contact volume is equal to, as I said before, a universal constant depending only on dimension times the area. For dimension 2, this is 2 pi times area. Okay? So in the end, Calabi is equal to 2 pi times area minus 2L mean square. So you see that right here I can tell you more or less how we're going to approach the theorem. If Calabi, so what does it mean for Calabi to be negative? Calabi being negative means exactly that the systolic inequality fails. That's negative, right? The systolic inequality fails. But now we're going to find, so if we believe in the fixed point theorem, this is going to imply then the existence of fixed points with negative action. But the fixed point is a fixed point of what? Of the return map. Then corresponds to a closed geodesic. And by this formula, the action of that closed geodesic is going to be its length minus L mean. So if this is negative, it's a contradiction to the definition of L mean. Done. That's the proof. So we have to, of course, work our way towards this final argument, but that's basically it. Okay. So let's prove this lemma. So the first step, so let me remove one point. Let's say that we're looking at this hemisphere. Let's remove a point on the other hemisphere. Let's look at everything, the complement of a point as R2, have some metric on R2. Here's an embedded closed geodesic, all right? We're shooting towards inside. A Birkhoff annulus corresponds to vectors pointing inside. So the first step is to show that, you know, every time I shoot, the first time I exit this hemisphere is giving me a, so if I shoot and see the geodesic segment looking at all the way up to the first exit point, I get an embedded segment. So this is always embedded. All these arcs are embedded. I should also mention that the return time and the return map, they both extend to the boundary of the annulus, because it's not clear, right? That, I mean, you have a return map and a return time for, you know, if you start shooting from vectors in the interior of the annulus, but in the boundary it's kind of unclear what happens. But you see, you know, what does it mean to return? Go up and go down. So if you go almost tangentially, you're getting, the return time is getting almost close to it's getting very close to this time to second conjugate point, and the return map extends to second conjugate point. Right? If you start shooting like this, you do this. So infinitesimally is just solving Jacobi differential equation, looking at second conjugate point and time to second conjugate point. So the first step in proving step one is to show that the claim that this is an embedded arc holds if you shoot tangentially, right? If you shoot tangentially, you're going to follow all the way to first conjugate point, because that's when you exit the top hemisphere, which means that you're looking at the first conjugate point. So I have to show that this arc is embedded, meaning that it doesn't self-intersect. So it means that this length is less than the total length here. Okay. How do you do this? So you just have to estimate the time to first conjugate point. So for this part, to normalize curvature between 1 and 4, first observation is that L mean is bigger or equal than twice injectivity radius, which is bigger or equal than 2 pi times square root of 4 in this case, if you want. Okay. Bigger, which is pi. Now let's look at differential equation for the variation as we start moving from tangential direction to inside. We get a Jacobi vector field, which is, you know, modeled by a certain differential equation, where k is the curvature along this arc. That's the differential equation that models the Jacobi vector field. The actual Jacobi vector field is this function times the normal vector, because you're just moving inside. And then, if you look at this complex number, let's say u, turns out that you have an equation where u is the symmetric matrix 1k, and which means that the argument d by dt of argument of u is equal to what? Cosine theta square plus k times sine theta square. Just do the math from this equation to this number. This number is just, you know, is a real part of u dot divided by iu, and then you do the math using this differential equation. You end up with this expression, from where you see that this number is between 1, let's say, argument of u prime is between 1 and 4. Okay? So what does it mean? It means it's bigger than 1. This means that if you look at argument of u at time equal to L mean, is bigger or equal than L mean, which is bigger than pi. So this vector, when you look at this evolution all the way up to here, it rotated strictly more than pi, which means that there was a vanishing of the real coordinate of the there was a if this rotates more than pi, what happens? It happens that there is a 0 of u before you hit this point back again. Okay? So first conjugate, this means that the first conjugate point before L mean. Okay. So that shows that if you shoot that this way or that way, you end up with an embedded arc. So now the next task is to show that you don't get self-intersections as you move the initial vectors. Okay? So what could happen here? It might be the case that you shoot and you're injective. Maybe you shoot, you have an interior self-intersection. So that's an open condition on the parameter theta. That's an open condition on the parameter theta. Or maybe you have a self-intersection exactly at the end point. Okay. But if you have, of course, at some point, if this happens at some point, it also happens in a situation like this without self-intersections, right? But then you have the length of these. So here is L mean. Let L be the length of this loop. So L bigger than twice injectivity radius. In this case is pi. L mean is bigger than pi. But L plus L mean is the boundary of this convex geodesic polygon. Okay, convex, of course, for this metric, which is less than or equal than 2 pi divided by the minimum of the curvature, which is 1. Okay, so I have a contradiction, right? So the set of these parameters, which is a vary on an interval, it's equal to the set of these parameters, because the complement of these parameters is open, but a set of parameters and another set of parameters, both are open, and one is the complement of each other, one of them is empty, but we showed already that for tangential direction it's non-empty. Okay. So step 2 is to show that there exists a smooth function taking values on between 0 and 2L mean such that if we write C of x theta equal to big X big theta, then big X is equal to little x plus rho of x theta mod L mean z, right? Rho of x0 equal tau of x0, rho of x pi equal to 2L mean minus tau of x pi. Remember that tau is the return time. So that's basically how we're going to know that there is an isotopy whose time 1 is psi, which is going to be in the kernel of the flux. All right, so let me first show the step 2 and then prove that this has the implications I just mentioned. Because you have injectivity for all this, because you have step 1, right? For all these rays, you have injectivity. You know that if you start from a point gamma of x, if you shoot inside, you're going to end up in a point gamma of x plus some function, whole one. This function is continuous and lies between 0 and L mean. Okay? The function whole one at x0, if you start shooting that way, it's going to be time, let's say tau 1, time to first conjugate points. Let me just write it like that. Time to first conjugate points. And if you shoot that way, you're going to end up somewhere. You have to be L mean minus time to first conjugate points. Right? If you go that way, you end up in a point which is given by gamma of x plus this. But this is L mean minus times the first conjugate point from that side. Right? Now you do the same argument for the outside. So you're going to have another function, ρ2, which is going to tell you that if you start from that guy, you end up in a point where the coordinates given by the addition of this point, of the coordinate on this point, plus something between 0 and L mean with the same properties. You do the same argument using the activity of the radius of the outer hemisphere. So here we have a function ρ1, and we're going to end up with a function ρ2 defined on the outer Birkhoff annulus with the same properties for the points outside, for the vectors pointing outside. So we can take ρ equal to ρ1 plus ρ2 composed at first heating vector. Right. So for a vector here, the function ρ we're talking about over there is going to be ρ1 of this point plus ρ2 of the vector you see here. That's a lift of the translation of the circular coordinate. So if you have a map defining the annulus, but you know how the circular coordinate gets translated, and you describe this translation by a real valued function, you're just singling out a lift of the map. Okay, that was step 2. And well, now there is a lift. I'm going to denote it by psi tilde. There is a lift with the following properties. If I write lift to the universal covering, if I write x tilde is a real value variable here, equal to big x tilde, big theta, then the translation is given by that function ρ. And we're allowed to project on the annulus here. Just a basic fact about lifting maps on the annulus. So if you can do this, you can also do, right? I mean, if you have a certain lift, you can also translate the lift by another period of the strip, and you get a different lift. So we can translate by taking away L mean. So this means what? This means that for the lower boundary component, we had this expression of ρ is equal to the return time, the time to the second conjugate point. So this is going to be time to second conjugate point minus L mean. That's for one boundary component. For the other boundary component, you get the minus sign here. That's here for theta equals 0. Here you get for theta equal to pi, right? Because we're taking away L mean from this expression. That's it. That's what's enough to show that the flux is 0, because the primitive of the one form of the area form you're looking at is minus. It was cosine of theta dx. So for theta equal to 0, this is just dx. And that's what you get. You know, if you integrate lambda on the path induced by this isotropy, you get exactly the x coordinate of the target, of the image of the point, minus the x coordinate of the initial point. So that's what you're getting here. So this is the integral. That's the right boundary condition for computing the action function. And you know, for theta equal to pi, you get a -1 here. So for theta equal to pi, here you have lambda equal dx, and here you have lambda equal to minus dx. So if you integrate minus dx, you get minus the difference of the x coordinates, right? So this expression shows that, well, actually doesn't yet show that the flux is 0, but it shows one thing. It shows that shows that the function tau minus L mean satisfies the boundary condition. Let's say P to upside tilde of P lambda. But it turns out that, I mean, it's then you have to recall a certain fact, which is that the return time also satisfies the differential equation we're supposed to solve. Right, that's a fact about Hebb flows. I mean, if you have a Hebb flow, you have a global surface section, the return time satisfies this differential equation. So in the end, this implies that this function also satisfies the differential equation, and it's given, and it assumes the right boundary values at the boundary of the annulus. Right? So the solution to our boundary value problem exists, and is equal to this. Now the flux 0 condition is equivalent to existence of the solution of the boundary value problem. So you get this formula and flux 0 at the same time. That finishes the proof of step 1. So then this means that we have the dictionary. I explain. 2 pi times area is Calabi plus 2L mean square. Okay. The final step is to show that we can apply the fixed point theorem, which means that now you have to guarantee that under a certain pinching condition, we have the monotonicity assumption that we need for the fixed point theorem. That's the final step. Okay. So if the pinching constant is bigger than a certain constant, which in the main theorem was 4 plus square root of 7 divided by 8, but now I'm going to make it a little bit better, then the return map is monotone. That's the final lemma. So for that lemma, we're going to use Gauss-Bonnet. So again, this is our tool, which is S2 minus a point outside of the hemisphere we chose, right? And we are shooting inside. We're shooting from a Saturn vector here. This is the angle theta. We're shooting, and you know, we look at the first hitting time, which is not the return map, right? Which is the map when the first time for which it leaves the hemisphere we chose. So to speak, sort of half the return map. Okay. So let me call this angle alpha 1. Sorry, not this angle, alpha 1. This angle, so this is theta, this is alpha 1, which is equal to pi minus theta. And this is phi, this is alpha 2. So Gauss-Bonnet says that 2 pi equals to the integral of the curvature on this region plus alpha 1 plus alpha 2. And alpha 1 is pi minus theta, and alpha 2 is phi. Okay? So if you want to differentiate the phi respect to, if you want to differentiate this angle respect to that angle, you're going to get 1 minus this derivative. Okay, so if we can show that this number is negative, so if we can show that this number is negative, we're going to be showing that as we increase theta, this number decreases. But then if you look again, what happens in the second half of the story, this increases, this decreases, but then the return angle increases. Okay. So what I'm trying to explain is that if this number happens to be negative, the derivative of the return angle with respect to the initial angle is going to be positive, which is exactly the monotonicity assumption. Right? So it suffices to show this inequality. And again, we have to appeal to Toponogov's comparison theorem.
Sorry, so what does the isotopy do? I'm confused. So you want to find the isotopy that ends with the time with first return map?
Yes.
Is there like a...
So we're using the fact that if we, singling out the isotopy is the same as singling out the lift to the universal covering, to the strip. But that was the previous lemma. What I showed is that you can find an isotopy. What does it mean to find an isotopy? To have a continuous periodic description of the translation of the x variables for the lifted map. So we want to find an isotopy. Suffice to find suffice to choose a lift or to find a certain lift. To do that, we have to describe a continuous translation of the first variable, and that's what we did. Now, why?
It's not coming from the annual time that you explained. Right?
No, that really came from Toponogov's comparison theorem, and that came from and once you have this description, this number takes value between 0 and 2 L mean, so this difference takes value between 0 and L mean. Okay, and this thing at the positive boundary, it was equal to just the time to second conjugate point. So if you take away M mean, you get this expression. This thing at the boundary shooting backwards was equal to 2L mean minus tau. So if I reverse the sign and subtract L mean, I get again tau minus L mean. Right. So this lift satisfies these properties on the boundary.
Okay, so it's enough to show that there is a layer.
With these properties, because this is a solution to the differential equation, and these identities here show that satisfies the right boundary condition. It's integral to the integral of, following the isotopy equal to the integral of the primitive of the two form. Which means this shows that this is the action, tau minus L mean, and flux is 0, both at the same time. Okay. So so the first step here is to differentiate this expression. We want to show that this is bigger than 1. So if you differentiate this, you work a little bit. I don't have time to show all the calculations, but in the end you end up with the integral. Let me, for a certain number theta here, let me denote this length by L theta, and let me denote this geodesic ray by alpha theta. Okay? So what you end up with is integral minus the curvature evaluated at, so let's say differentiating at theta, doesn't matter, times u of s ds, where u of s is the description of the Jacobi vector field of this variation, right? This is a variation from where you get the Jacobi vector field, which vanishes here, and it's everywhere normal to this velocity vector. So you get an expression of this kind, and this is the positive perpendicular vector to alpha dot. All right, you have a differential equation of this kind here. Right. Okay. So if you substitute this ODE, you're gonna get u double prime, right? So this thing is equal to what? Actually, you get minus. So yes. Actually, there is a mistake here. Here's a plus. So here you get a minus. So what you get is u prime at 0 minus u prime of L theta. And this is equal to 1 because this is a Jacobi field that comes from a variation where the fixed point, the base point is fixed, so just rotating the unit vector like that. So we have this initial condition for the derivative. And we want this to be bigger than 1, so if this is equal to 1, we want this to be negative. So you want to show that the Jacobi vector field, when you look at what happens in this point, it's pointing to that side. That's all we need to show. So again, if we look at the argument of this vector, let's say beta, we get an expression beta equal to cosine of beta square plus k sine of beta square. Now normalize. So sorry, curvature is to be between delta and 1. So this number here is between delta and 1, which means that beta of L of theta is what? Is between delta L of theta and L of theta. Right? So what? We want u prime to be negative. U prime is the first coordinate, is the real part of this vector. So if we can be sure that its argument is between, let's say, pi over 2 and 3 pi over 2, then the first coordinate is going to be negative. Okay? So we should estimate this to be at least pi over 2 and this to be no larger than 3 pi over 2. That's the estimate we need to make. For the round sphere, This is exactly equal to pi. Beta prime is exactly equal to 1. You know, the integral we're trying to make to show this differential, which we want to show, this number which we wish to show, it's at least equal to 1 for the round sphere is equal to 2. So everything makes sense. All right, so now we have to make an estimate. We want delta times, so let's recall what's L theta. L theta was this length. Here's theta, right? And we want delta L theta to be bigger than pi over 2 and L theta to be less than 3 pi over 2. That's what we want. We want to force a condition on delta. So now let me denote this length here by L1 and this by L2. So using Toponogov and Klingenberg at the same time, you get for L of theta plus L1, L of theta plus L2, and L1 plus L2, you get an estimate between from below equal to 2 times the conjectivity radius, which is at least equal to 2 pi. And from above, but that's Klingenberg, that's Toponogov here, we're going to get 2 pi divided by square root of theta. So, right, in particular, if you reverse the sign on for the last guys here, you get these estimates. So this means what? This means that L of theta, which is 1/2 of 2L of theta plus L1 plus L2 minus L1. Okay, let me write it like this. Silly way of writing L of theta. But then you add 2 of these estimates and subtract this one. So you're going to get 4 pi minus 2 pi. Actually, I have to not divide by 2. Square root of delta. From here you get 2 pi square root of delta minus, 4 pi square root of delta minus 2 pi. And finally you get this. 2 pi minus pi divided by square root of delta, and here you get 2 pi divided by square root of delta minus pi. So that's the estimate you have to satisfy. So you see that it is satisfied for delta equal to 1, right? For delta equal to 1, you get pi and pi. Pi is a number between pi over 2 and 3 pi over 2. So you see that the game is now just to see how much can you relax delta in order to keep this. And then what you see is that if you do 2 pi minus pi square root of delta is at least equal to pi over 2, you cancel, you get, if you call x square root of delta, you're getting sorry, there is a delta here, right? There is a delta here. So delta. This is equal to 2x squared minus x minus 1/2 bigger than 0. So the roots of these are divided by 2 times the coefficient of x squared, right? So you get 1 plus or minus square root of 5 divided by 4. So luckily for us, there is a positive root, and this positive root is less than 1, right? The positive root is 1 plus square root of pi divided by 4. So as long as square root of delta is bigger than this, we get the monotonicity assumption. So this inequality is enough to guarantee this monotonicity assumption. And this number is about 0.765 something. So this pinching condition guarantees the systolic inequality. The other inequality will tell you that delta has to be at least equal to 0.64, which is smaller than this. So this is enough for the systolic inequality. So actually, the pinching condition I stated in the main theorem was not better than this one. So it's like improvement of the pinching condition. So I don't know how to make this proof only work in the Riemannian side, and I also don't know how to make this proof only work on the symplectic side. I cannot avoid using, these comparison theorems, and also cannot just work in symplectic from Riemannian geometry, right? I have to make use of this input from the fixed point theorem. So I guess I'm out of time. I won't have time to discuss all the other things I plan to, but at least I was told that in this seminar we're supposed to prove something. So, okay, sorry, that's what I did. Sorry. Okay, thank you.